So Lali, can I have the next slide, please? Thanks. So I'll start by introducing myself. I'm going to be your chairperson today. I'm Carol McSweeney and I'm the Deputy Science Lead for the UKCP Climate Projections Programme. And I'm pleased to say we've got two really interesting speakers lined up for today. So welcome to Hamish Wilkinson from Fathom, who's going to be talking to us about grid-based extreme water level modelling in the British Isles. And also to Mike Sanderson from the Met Office, who will talk about present day and future wind-driven rain in the United Kingdom. And we'll have some opportunity for questions at the end. And we just have the next slide. Okay, so just a few points of order to help this morning run smoothly. So each presentation will be followed by a Q&A. So please do post any questions that you have in the Q&A box. And if you can upvote those questions other people post that you think are interesting, that will help me to identify some of the top priority questions to put to the speakers. As attendees, all of you will remain muted unless I enable you to speak. The webinar is being recorded, as I've mentioned, and that recording will be shared on the Met Office Science and Services YouTube channel. If you have any technical difficulties, please do contact us using either the chat function in this Teams meeting or using the UKCP user network and Met Office email. Okay, I think with that, I'd like to introduce our first speaker. Just to say a little bit about Hamish's background. Hamish is a scientific model developer at the flood modelling company Fathom, and there he works primarily on the coastal modelling and terrain teams. Hamish's background is in the geographical sciences with a BSc in Earth Science from Swansea and an MSc in Climate Science from Bristol. Previously, Hamish has worked on other natural perils, notably subsidence, landslide and coastal erosion while at terra firma. And today, Hamish will focus on the work he did for his MSc thesis using UKCP 18 climate projections to project changes in storm surge. Okay, so with that, I will hand over to Hamish. Over to you.
Cheers, thank you very much. Yeah, so hello everyone. As introduced, I'll be talking about grid-based extreme water level modelling in the British Isles. I think it's worth saying to start with that this is not a model that's used by Fathom, but it is linked to UKCP 18. So I thought it'd be interesting to have a chat about and kind of give people an insight into how you can use the data sets to produce other data sets and other models. So without further ado, I guess, I mean, the big question to start with is why do we care? And particularly, why do we care about climate change and its effect on extreme water levels? So kind of if we step back from the actual modelling and look at the bigger picture, there's a few things going on in kind of the broader climate system that are relating to changes in storminess, essentially, here in the UK and the British Isles. And there's quite a lot of well, I guess scientific debate about whether changes in storminess will be significant. And I think there's debate about whether it's going to get stormier, less stormy, whether we're going to have fewer big storms, more little storms, etc. And these are kind of all linked to these processes that I've got here on the slide. We've got Arctic amplification, AMOC, which is Atlantic meridional overturning circulation slowdown, which I'll only be saying once, AMOC from now on, and North Atlantic oscillation. And these are kind of bigger kind of climatic trends. So to give a really quick overview of these, Arctic amplification is the warming of the Arctic, twice the global mean. There's a few different reasons for this. One of the most simple to kind of explain is albedo decline, which is where you have ice melt. Ice is very reflective. When it's gone, the light, the sun, well, the radiation is not being reflected. So there's more heat basically absorbed by the ocean, which then radiates that heat back into the atmosphere. So the Arctic gets warmer, we have more ice melt, and this melt freshens the Arctic Ocean, and this has knock-on effects for AMOC. And AMOC itself is, I guess you can kind of think of it as the Gulf Stream. People tend to be more familiar with that. So the Gulf Stream is one part of AMOC, and kind of on a very simplified way of viewing it is you have warm water flowing up from the tropics to the Arctic, where it gets colder and denser, and it sinks, and then it travels all the way around the bottom of the ocean back up to the tropics, where it's sucked, for want of a better term, back up because the water on top of it is moving up north towards the poles. But it's a thermohaline current because it's based on temperature and density. So if you imagine the Arctic melt that we just talked about freshens the polar regions, and because of that, the water there is less dense. It's also warmer, so it sinks slower, so that slows the whole process down. When this actually results in, if it slows down, you get less heat transport up kind of north. And this has an effect on temperatures and the temperature differentials between the north and the south, which in turn affects storm tracks here around the British Isles. And the North Atlantic Oscillation is basically part of this. So without really getting into the weeds, if you basically just imagine this as like a pressure difference or a temperature difference between the north and the south, the stronger that difference is, the stronger the jet stream is generally. And when the jet stream is running faster, it tends to straighten out. You get less kinks. So we actually have more no, we don't. We have worse conditions. We tend to get more storms. When the pressure differential is lower, there's more kinks in the jet stream, and we get blocking patterns, and these produce kind of more settled weather. So it's that temperature differential which is affected by kind of a variety of different factors. So AMOC slowdown would result in it being colder basically up where we are, and then it's in comparison that differential between where we are and the tropics is stronger, so we might get more storms. But with that said, there's a lot of uncertainty in all of this. These are long-term patterns, decadal patterns, and we don't have all the data yet, so we can't really know. And this has a knock-on effect for uncertainty in projecting extreme sea levels. So that's basically why it's worth looking at, because we're not really sure. So it's an interesting topic. And yeah, with a very brief background there, and I appreciate probably too brief in some ways, but anyway, moving on. The idea is to take the UKCP 18 climate projections, because modelling all of that stuff I've talked about is very difficult. So I didn't do any of that. I left that to people know how in the Met Office. I took their data sets basically from UKCP 18, and I ran cell-by-cell calculations between a grid, if you like. So if you imagine, if you have a grid and you lie another grid on top of that, you can then do calculations on each of those grid cells between different data sets. So that's what I did. The model itself has 3 distinct models. We've got modules. We've got the surge module, the tide module, the wave module. This is all on a 12-kilometer resolution. So it uses the UKCP 18 local, I think they're called, which is at 12 kilometers. And it's pretty computationally efficient, which is a plus. It's not a dynamic model that you might see others running. Global climate models, they tend to be dynamic. You also have a lot of dynamic surge models as well, but this is not one of those. This does calculations purely on a cell-by-cell basis. And this is kind of what the data sets, if you're not familiar with UKCP 18's gridded data sets, kind of look like. So you have one data set, which you can see here is the Americas, and then below that, and you can imagine the top tile, for example, is made up of many grid cells, and then below that you have a time dimension. So essentially you have all these layers stacked on top of each other, and in that way you can do calculations across broad ranges of time and get a really good look into the future. So for this, I used UKCP 18 for wind, sea level rise, that is, and extreme still water pressure, and these are all in NetCDF formats. For ERA5, I used swell and wind wave, and we'll get into why I used that later. And I also included gauge data, British and Irish, and this is kind of a point data set, which you convert to a grid. And then bathymetry was GEPCO, which is a global terrain data set underwater, if you like. So how do we do it? First of all, the tide module. I'll be pretty brief because this is not particularly interesting, to be honest, and not all that linked to UKCP 18. But from the tide gauge data, you can detrend that to get a picture of the tidal year. And then you can match that up to UKCP 18. So you can actually simulate tide for each day that UKCP 18 simulates, and then feed that into your water levels. The wave module is a little bit more interesting. And I appreciate if you don't like maths, equations like this can look quite scary. And to be honest, I'm not very good at maths either, so I would agree with you. But the lovely thing about this is the computer does all the maths for you. You only need to write this out once and then stick the inputs in. And the inputs that we get are basically wind velocity and direction. And we can derive these from the UKCP 18 datasets they provide. And we can then we can gather the fetch, which is the distance the waves run over the water, which is also part of this this equation here. And from that, we can basically generate an approximation of wind wave on a cell-by-cell basis. That's significant wave heights, offshore wave heights, to give us a water elevation. And we can use GIBCO for depth there. And then this lovely drawing I have here on the side is basically something I made in Paint, which is attempting to show the quadrants, if you like, that you would get in each cell of the grid to calculate what direction the wind is coming from, and the fetch from there is because that would run into land, if you like, and such, and it gives the distance the fetch runs over. So that gives you local waves, basically. But anyone who spends any time at sea will know it's often quite confused. And you have what's called a wave spectra, where basically you have more than one kind of wave in any kind of given area of the sea. You have local wind wave, which is produced by the wind blowing over the water. You also have swell, which is produced from distant systems. And these all kind of mix together, and you often have a wide range of spectra in a given wave sea. UKCP 18 is over the British Isles. You can't actually produce swell from them directly, although you can produce wind wave. So what these diagrams are basically showing is we have this reanalysis data set, ERA5, which we can also tie into a model. But that doesn't project into the future, because the reanalysis data set is basically a look into the past, what's happened beforehand. So we can take what we know from the observed record and basically plot a linear trend on it, which is what we've done here. And you can see that there appears to be a slight increase in swell, a slight increase in storminess. This is what the graphs with the lines are showing across different seasons, the scatter graphs, those are, sorry. This isn't exactly conclusive, but there is some literature to back it up. And we do want to project, swell into the future if we're using the UKCP 18 future climate data sets. And it'd be a shame to miss it out. So what we've basically done here is we've taken this linear trend, applied it on a cell-by-cell basis, and uplifted the observed ERA5 record. And then we can use that into the future by basically doubling it up. It wasn't the neatest way to do it, I will admit, but sure, that's the way it goes sometimes. And you can see these bar charts basically just showing the shift in distribution, which that gives us, which then allows us to add swell into our model. So we're now considering wind wave and swell to give us an approximation of the wave spectrum and the uplift that has on sea levels due to storminess. And then no kind of extreme water level model would be complete without surge. So we do this in quite a simple way. These are some quite classic equations here. And again, they don't look nice, but what this basically says is that you get an uplift of water when wind is pushing water along the surface, which is wind drag. And the shallower it is, the more it gets pushed. And then the narrower an opening is, the narrower the geometry, if you imagine, the more the water's shoved and piled up against that boundary. And you end up with dynamic amplification, it's called, but essentially it's surge. This formula, though, it does amuse me slightly because it basically assumes every grid cell is like a swimming pool, if you like, with square edges. And it doesn't consider coastline geometry or anything like that. It's quite a simple method, but it is computationally efficient and it works on a grid by grid basis. And I think it's worth saying at this point that each grid cell doesn't actually run into the next. So you don't, for example, proper dynamic simulations will conserve mass and momentum and such. They'll basically make sure that if you're moving from grid cell A to grid cell B, and you only have 1 meter of water in grid cell A, you can't suddenly have 20 meters of water in grid cell B. This doesn't do that. It works on a cell by cell basis. So there's definitely limitations to this model. But luckily, the input data sets, the UKCP 18 ones, do all that clever stuff. So you can kind of include it implicitly because they do all the work for you, which is nice. And the second one here, the inverse barometer model, that's basically saying that below a certain pressure, I think it's 1,013 millibars, every millibar you drop below that pressure, you get an uplift. Well, I think it's a centimeter, but I'd have to actually check, so don't quote me, of sea level rise. You can also include that static uplift simply from the pressure field of the storm moving over the area. And if you're not aware, storms essentially are areas of low pressure. So the bigger the storm, generally the lower the pressure within, the more static amplification you get. And of course, the bigger the storm, the more wind, the more dynamic amplification, the more wind, the more waves, et cetera, et cetera. It all feeds into each other. Yes, that was a bit of a whistle-stop tour. So I quite like this figure, so I put it back in. And you can basically see the methods we've gone through there in the surge module. We've got the inverse barometer model. We've got Harris's methods. We've got the tide module, which you really skipped over, but that's fine. And then the wave module feeding into that as well. And these give us at the end extreme still water levels and extreme moving water levels. So the extreme moving water levels are here characterized by the ones that include waves, and the still water are just including the effects of surge. And both of those include tide. You'll also see down here, kind of on the left and the right, you've got sea level rise, and these are just tacked on at the end. And again, I'm pretty certain I got the sea level rise data sets from the very helpful people at the Met Office again. And part of the reason for tacking this on at the end is it means you can look at changes in surge and extreme water levels based purely on storminess alone. So if we're getting more storms, because obviously extreme water levels are going to go up because the seas are rising because of climate change regardless. So the interest here is primarily on storminess alone. But I did whack it on the end because who doesn't love a disaster scenario? It always looks good. And I think I should say as well, this is using, I think it said in the first slide, but RCP 8.5 climate projection, which if you're not aware is one of the, it's basically one of the worst. I think it might be the worst. But again, disaster scenarios are much more fun to model. So how do we do? Validating models is quite boring, but it's always quite important as well. But I won't dwell on this for too long. This is looking at RMS, a root square mean error, and it's in the units that the measurements are in, so meters in this case. And on this drop down on the left of swell, basically we're doing really quite well. The errors are really quite small. I actually can't read my own color bar there, but they're really, really small errors. And that's because I've applied a linear regression on the ERI5 reanalysis. And this is, I think this is one of the early time steps. So if it wasn't really good, there'd be something really wrong. So I can't really take so much credit for that. The wave RMSE, here we're comparing my computed wave outputs using the swell methods we described, no, not the swell, sorry, the wind wave. So this is using Brett Schneider's method, probably saying that wrong, to calculate wind wave. And we're not doing so well here. I think we've got errors, again, I can't really see it, but much higher, but we're generally doing better on the coast, which is kind of good, but we do still overestimate the extremes of wind waves at the coast. I would guess this is because of a lack of nearshore processes. This is offshore waves that the calculation does. And also ERA5 is not in itself the best model in the world. It's quite a coarse resolution, as you can see from the swell. That's why it's the British Isles have kind of been butchered. I think it's 35 kilometers or something. Surge was generally much better. RMSE between 0 and 1 meters. There's a shocker in Blackpool. I think that's because Fetch runs straight into the Isle of Man, so it doesn't really get much in the way of a dynamic amplification. Tend to overestimate surge overall, which I didn't expect. I expected negative bias because coastline geometry is pretty important for dynamic amplification. So something's going a little bit screwy here, but I think it's probably because although I calculated tide, I didn't actually include it in the dynamic amplification calculations, which matters because basically the height of the water, if you like, has a significant effect on the amount of surge you get. The more shallow it is, basically, the more surge you will get. And if you don't add the height of the high tide, which is what everything else is run on, to that, which around the British Isles can be a couple of meters, then you're artificially ramping up surge. And I did do that deliberately because A, who doesn't love a disaster scenario, and B, I thought we would underestimate surge, but it actually turned out the other way around. But you know, them's the breaks, you've got to move on. This stuff is, how much time? We're pretty tight for time. This is basically a ring around the UK of points, and you can ignore the top one because we did an ensemble, but that's a bit in the weeds. The bottom one is basically comparing this model we've been describing to two of the Met Office models, HADGEM and MPI. And kind of in the ballpark, this is a trend year on year, I should say, of millimeter increase in surge. And as you can see, we're getting absolutely whopping 0.2 millimeters year on year increase in surge. So it does beg, what's the point of doing all of this work if actually surge barely changes? And we're within the two most extreme, I picked these because they're the highest and the lowest, were the most extreme Met Office models. But not actually matching either of them all that closely, which is perhaps not a good sign, but their models, you know, have big teams and are probably much better than this one, and I suspect are less computationally efficient. So we're doing all right, particularly when given, this is just the same slide with the 20-year level. You can see it's mattering a little bit more now. In some areas, you know, you're getting up to 2 millimeters of increase year on year. So, you know, by 2100 or what have you, you might have, well, still not much in the way of increase. Like 5 centimeters, maybe. It's not very much. But in terms of model agreement, the Met Office models wildly disagree with each other as well. So the fact we're in the same ballpark of them is useful to a certain extent. And BIS does largely, as you can see in these ones, track positive. It's always saying there's going to be a slight increase in surge due to storminess. This is for still water levels, incidentally. And some of the Met Office offers say that as well, although it does vary around the coast. These are ports down at the bottom, incidentally. I should have said that. And then extreme moving water level is a little bit more interesting. We're actually getting more surge here. I'm going to really fly through this now because time is of an essence. But there is a noticeable uptick, really. Again, this is in millimeters, but you know, 5 millimeters per year does add up over time. So there does seem to be an increase in wave activity. And when you add sea level rise on top of that, you know, it starts to become a little bit more scary. Although I should say that these moving water levels are offshore conditions. So it's not actually fair to apply these to the coast. You wouldn't want to force a flood model with these outputs, for example, because really you should perform shoaling and such on the waves. But for a comparison to what it's like now, to what it's like in the future, I think it's a fair use. But certainly if you wanted to use this for flooding, then you would definitely want to shoal the waves. To give you an idea, I think a lot of papers take 20% of offshore wave height and use that as the wave setup you would actually get at the coast, which matters for flooding. And I think that's me. I appreciate that was quite quite rapid. I should maybe have cut that down a bit more, but yeah, any questions, I'll be happy to take them.
That was great. Thanks, Hamish, for a really interesting presentation. We've got a couple of questions in the Q&A. If anybody else has got any others, then feel free to type those in as we answer the first one. I'm going to go to this question from Matt Miller first because it's been upvoted by somebody else. And Matt says, Putting it simply, would it be fair to say that these models indicate the impact from changes in sea temperatures from more greenhouse gases, and what that does consequently to the ocean ecosystem or ecosystems?
I'm not an ecosystem person, but I'll answer best as I can. Certainly, the oceans are warming. Yeah. Storm generation is basically, the more warming you get, the more energy there tends to be in the atmosphere. So the stormier it tends to get. And this is a huge, broad oversimplification, but in general, that is correct. In terms of ocean warming's effect on ecosystems, it would certainly have an effect, particularly when it's happening fast, because biome shift, if it happens too quickly, can cause species to get extinct. But if you're worried about ocean ecosystems, I would argue that things like ocean acidification, which is the uptake of carbon into the ocean, is probably more of an issue on a broad scale than simple warming is. But I'll leave it there. I'm not really an expert in that area at all.
Thanks, Hamish. And as we've got a couple more minutes, we'll go to the second question, also from Matt, around the AMOC. Matt says, would I be right in thinking that the straightening of AMOC stream is similar impact to straightening of streams and rivers on land? As such, would it be putting it too simply by saying we need the curve to reduce impact?
I wonder if there I was maybe tripping over my words. So the AMOC itself wouldn't straighten. The AMOC would perhaps weaken, which would reduce the transport of heat from the tropics to the poles. So it would be a weakening or a shutdown of AMOC we'd be worrying about. I think you're probably referring to the jet stream, although I may have, again, tripped over my words. That's maybe on me. So when the jet stream is straight, you basically don't have, they're called Rossby waves, but the Rossby waves essentially produce blocking patterns which force storms either above or below the UK. When the jet stream is straighter, which happens when it's very hot, say in the tropics, and very cold in the poles, you get a strong pressure differential, which increases basically the speed or the strength of the jet stream, straightens it out, and we tend to get more storms. In terms of what we can do about that, and not much, to be honest. Use less fossil fuels.
I guess that also depends, sorry, just taking the chair's prerogative here, on what kind of impacts you want to reduce, because although if you've got quite a jet stream bringing storms, if you're worried about storm impacts, maybe, but the waviness has different impacts in terms of perhaps bringing more settled conditions, cold snaps, droughts in the summer. So yeah, depends on the impact, right?
Yeah, for sure.
Okay, thanks ever so much, Hamish. Thanks for a really interesting talk and for answering those questions. Let's move on to our second speaker. I'm going to introduce Mike Sanderson. So Mike works at the Met Office. He's a climate scientist with a background in chemistry. Mike works on projects for a wide range of customers to help them understand their vulnerability to climate change and climate extremes. He's led work on climate uplift factors for Network Rail, which were used to assess changes in the failure of line-side equipment and overhead power lines. His interests include the impacts of climate change on urban environments, health and infrastructure. And he's going to talk to us today about some new data he's been deriving around wind-driven rain. So over to you, Mike.
Okay, thank you, Hella. Excuse me, sorry. Thank you, Carol. Just moving, yes, there we are. So yes, I'll briefly introduce this topic. I'll describe how we quantify wind-driven rain, and then I'll briefly go over some of the impacts of climate change on wind-driven rain, and then summarize results at the end. So before we go any further, think, well, what exactly is wind-driven rain? Well, it's exactly what it sort of says on the tin. It is rain essentially given a horizontal velocity by wind that then falls obliquely. And obviously, under such circumstances, some of that rain will strike a wall. And that's an important source of moisture. Under certain circumstances, this wind-driven rain can penetrate the walls, leading to things like mold growth, which is shown by the image in the top there. It can also enhance the failure of brick and stone. There's been, for example, I know a lot of work on the impacts of wind-driven rain on the facades of colleges in Oxford because of the type of stone they're made of, that these freeze-thaw cycles can be quite damaging to the fascias there. And these images here show other problems with such as the growth of algae. There's also a newspaper article a few years ago as well discussing these impacts of wind-driven rain. And in the third climate change risk assessment, there was a risk labelled H5, which is the risk to building fabric, and wind-driven rain was particularly noted in that assessment as one of the areas that requires further investigation. So that was one of the motivations for undertaking this work. So what do we know about wind-driven rain? Well, way back in around the 1980s, and before that, there was some research done on the wind-driven rain using special rain gauges that would measure the wind from different directions. And a wind-driven rain dataset was created for the UK. So it was derived from around quite a small number of weather stations, though a much larger number were used to look at the proportion of winds from different directions. And it was based on some older data recorded over this period here. So this is a study useful data set. It's not fully now representative of the present day climate. We know rainfall extremes and so on have increased since this period. And additionally, this data set doesn't contain any information on possible future climates, which of course is also going to be very useful for the building industry. So there's a British standard on wind-driven rain, this one here, BS 8104, which is based on these data, and this remains current. There's also in the building regulations this document called Approved Document C that contains a diagram showing the UK splits up into 4 different zones of wind-driven rain. And these are used, for example, to assess whether cavity wall insulation is appropriate. So in the zones in this diagram 12 where wind-driven rain is very high, it's generally considered that cavity wall insulation is not an appropriate way of reducing the energy consumption of a property, because under certain circumstances, the cavity wall can actually act as a wick and draw the moisture in for the outside wall into the inner one and cause some of those problems that I showed in that earlier figure there. There's also this other ISO standard, which is sort of more or less based on 8104, which is also used. But there's clearly a need to update the data and the maps here. Yeah, so how do we quantify wind-driven rain? So we're using this wind-driven rain metric from this ISO standard here, I'll describe shortly. It's calculated on hourly timescales, and it's, as you would expect, a function of the rainfall amount, precipitation, the wind speed, the wind direction, and also the wall orientation. And generally with this metric, higher values mean more wind-driven rain striking a given wall. So we calculated the wind-driven rain metric for 8 directions. So that's essentially north, northeast, east, and so on, all the way around to northwest. There's nothing special about this. It was a pragmatic decision based on the quantity of data this project produced. Ideally, we would have used a larger number of directions, but as I say, that just wasn't possible. So this is the equation used. It's fairly simple. So it's simply a product of V, which is the wind speed. R is the rainfall amount, and D minus theta is the angle between a given wall orientation and the wind speed. So essentially, it's just saying if this cosine is greater than 0, that means the wind-driven rain will strike a wall at some particular angle. So therefore, wind-driven rain will be present on the wall. When it's less than 0, we assume there is none. This is clearly quite a simple approach, but it's currently one of these industry standards, so we've stuck with it. So we can calculate a few metrics from this. So sorry, I should say we count this I value here, this wind-driven rain metric on hourly timescales as these units of litres per square metre per hour. We can calculate the annual totals to get an idea of what the total is in a year. We can then calculate this quantity I as prime, which is the sum of I over individual spells. So how do we define a wind-driven rain spell? Well, we use it as simply a period where this value of I is greater than some quite small value, and they are separated by 96 hours or more. Some research was done years ago that suggested walls would dry out in a period of about 96 hours. So if they're separated by 96 hours or more, then we treat them as individual spells. So which data we use? Well, we're using the UKCP 18 data, specifically the new 100-year kilometre scale projections, which were completed in March of 2023. So the original model has a resolution of 2.2 kilometres, 12 ensemble members, and then the data over this 100-year period shown here. And the future projections are only available under this high emission scenario. So to help make our life easy, because we're doing a UK study and to help comparison with other UK data sets, the producers of the UKCP projections have aggregated these data from the models grid onto this 5-kilometre grid on the OS national grid. So we've used the 5-kilometre data for that reason. We're going to focus on a baseline period shown here and the times when the model reaches 2 degrees and 4 degrees of warming above pre-industrial levels. So what are the impacts of climate change? So we calculated the annual index that I showed earlier for the baseline of these two periods here. We looked at the ensemble mean and the standard error in the mean, and then we sort of plotted these as a function of wall orientation. So that shows the results here. So what I did, I calculated these wind and rain metrics for at the locations of the various weather stations around the UK, which just show that the names are shown on the top left of each of these figures here. So we look at an annual changes only. We can see these values over all 3 time periods overlap quite considerably, although there is suggestion we see the highest values under the 4-degree scenario. But if we look at different seasons, we can see quite different result. So if we focus on the summer first, we can see generally there's a projection that the wind-driven rain will decrease in the summer. You can see as we go from the sequence baseline in red to 2 degrees C in purple to 4 degrees C in green, you can see particularly for the sort of south to west orientations, you can see in a number of these locations, the wind-driven rain does decline quite notably, but not everywhere. So for example, in Stornoway, even under 4 degrees, the model is projecting very little change, where in other places like Nottingham and Valley in Wales, you can see there's some quite large changes projected by the models. So generally see the biggest decreases from the westerly and southerly directions, which perhaps we might expect, as that's where the majority of our weather comes from in the UK. At least the wind and rain tends to come from those directions anyway. And clearly these changes are not uniform across the UK. We do look at the same data now for the winter. We can see the opposite effect. We can now see an increase in wind-driven rain, mostly from these south and sort of westerly directions here, more or less at all locations, although the number of events from easterly is relatively unchanged, although it's perhaps a small decrease. And these changes are a little more spatially consistent than we saw for winter. So another way of looking at this is look at the percentage changes. So again, I've got the same weather stations listed here. This is just to show this. So again, we can see the annual changes, not much is happening. If we look at the changes now for spring and autumn, we can see there's not a lot of change projected by the models. Whereas if we look at winter and summer is where we do see the big changes. And I should say these pairs of data, the left-hand column of points is for 2 degrees warming and the right-hand column is the change for 4 degrees warming. So we can see some quite big changes in winter, but even larger decreases here in summer. So that's where the climate impact is really being seen in this, in the winter and rain data. We also looked at the magnitudes of 1 in 3 year wet spells. Now this is used in the industry as to sort of assess zones of wind-driven rain and whether things like cavity wall insulation is appropriate and other things too. So we did calculate the magnitude of a 1 in 3 year wet spell and how that might change. So I've got the baseline here now. I've just got the changes for the 4 degree warming shown on the right hand side. So generally, you can see if we look at the different wall orientations, not surprisingly, we see the largest values of these 1 in 3 year wet spells on sort of west facing coast, particularly in Scotland, and then much smaller values for wind-driven rain for the north and northeast and so on. But but the model suggests actually these 1 in 3 year wet spells will actually reduce in magnitude over large parts of the UK from most sort of north and easterly directions. There was a small increase projected in some of the south and west areas here. It showed it varies, particularly in the coastal locations in the sort of west, country down here and in Wales. So again, we're seeing sort of perhaps some interesting differences in different parts of the UK projected by the model. I'll just summarise that then. So we've calculated the wind-driven rain index then for the entire UK for these 3 different time periods. I haven't shown it, but we did thoroughly evaluate the model wind-driven rain using hourly data from, we started with 18, we did actually in the end find 30 different weather stations to evaluate the model, and you have to take my word for it, I know, but the evaluation was good, actually show the model was doing a good job. And our initial results show that there is increased wind-driven rain in the winter months, especially under the 4-degree scenario, but clearly reduced amounts in the summer months. And there's little changes projected in spring or autumn. And so far, although we haven't delved into this in great detail, these changes in wind-driven rain appear to be mostly driven by changes in rainfall rather than wind speed, although we would need to do some more in-depth analysis to see if there are any subtle changes in wind or proportions of winds from different directions. There's a report on this. The work is due to be published by DESNESA hopefully later this month. It might be early March. We've also uploaded some of the data files we produced onto the CEDA archive, and these will be released once this report has been published. But there are a few caveats. First of all, that wind-driven rain metric I showed earlier on, having found some reports on the earlier studies of wind-driven rain, it does appear to be been derived probably in the 60s or 70s from some quite limited measurements of raindrop sizes and their terminal velocities. So, and that was only for sort of valid for certain intensities of rainfall. So one thing that might be interesting to do is to get hold of some other data for different rainfall intensities, that is the raindrop sizes and the terminal velocities, and then adjust that metric depending on the rainfall intensity. So that might give us a slightly more accurate estimate of the amount of wind-driven rain. There are other methods for quantifying wind-driven rain. So some of the early studies, some of the real pioneering work by this chap Lacey in the 70s, he used this omnidirectional index, which is simply a product of wind speed and rainfall amount. So that's a simpler approach. Other people have used classified 12-hour periods of wind-driven rain as whether moistening, drying, or neutral. And they just looked at wind directions within plus or minus 60 degrees of a given wall orientation. So they didn't use a cosine in their calculations. And another person's simply sorted the wind directions of bins, in the particular case was 16 different directions, and then just used the product of wind speed and rainfall amount for each of those orientations. So again, they're similar, but these all probably give perhaps slightly different estimates of wind-driven rain and so on. So it's just to point out there are other ways of quantifying wind-driven rain. And obviously for this particular study, we've only used data from a single climate model. So it may be that if we had high resolution results from other climate models, they might project different climate impacts to what we've seen from UKCP 18. So that's something else to bear in mind as well. I'll stop there, and that was a bit quick actually. I'll stop there and take any questions.
Thanks, Mike. Thanks for another really interesting talk. I'm just having a quick look at the Q&A. We've got a couple of questions. Again, thanks, Matt. So this question says, Mike, would I be right in thinking we need to be more concerned about signs we need to get indications of what things are looking like for the height of the warm or cold seasons then? So I think Matt is asking, should we be particularly concerned about the change in wind-driven rain in the summer and winter seasons at the height of those seasons?
Probably, yes. Certainly where we're still seeing the models are projecting the biggest impact, so particularly in winter. So that's certainly yes, that's probably the areas to focus on. In fact, another thing when we did this work we didn't have a really time to go into is having talked to some of the owners of particularly heritage buildings like the National Trust and others. One of the things they're interested in is, do these zones of high wind-driven rain change in the UK? So, for example, buildings in the west where you would expect large amounts of wind-driven rain are highly susceptible, and they're generally built to withstand it, whereas they say their buildings more in the east, say East Anglia, aren't, because they don't get that. So if there's, say, a sudden change and those buildings in the east are getting hit by a lot more wind-driven rain, that would be a real problem in sort of how to future-proof them. So that's another sort of subtle aspect we might look into under climate change. Is there any obvious shift in those zones of high wind-driven rain? But say that sort of was outside the remit of this particular project, but would be something interesting to look into in the future.
That's fascinating. Thanks, Mike. We'll go to our next question. So thanks to Megan Pierce for this one. Megan says, thanks for the presentation, really interesting. How much of the climate signal do you think can be attributed to changes in rainfall versus wind, i.e. the individual components of the metric? Were you surprised by any of the signals for certain wind directions?
Right, I haven't looked into changes in the wind directions per se. We did look at projections of just absolute wind speed, and there's very little trend in that projected under UKCP 18, whereas we know there is more generally, as a sort of broad brush, more rainfall in winter and less in summer. So that's, at the moment, it looks like the changes in rainfall are a primary driver of those climate signals we see. But as I said, if we'd had more time, we would have liked to have delved into perhaps looking at weather types, or changes in wind direction or proportions of wind from certain directions a bit more. But let's say so far, from what we gather, I think the rainfall is the primary driver, but there could be a small secondary contribution from changes in wind speeds and directions too, but we haven't had a chance to really delve into that.
That's great. Thanks, Mike. As we've got a few minutes, I'm going to take the chairperson's prerogative and just ask one more question. I was interested about your point about just being based on one model, Mike, and wondered if there's anything that in particular we know about the characteristics of those UKCP projections that might be different from other models we could use. So I guess I'm asking, what do we think we might see in terms of differences if we were to run it with some of the other models?
I'm trying to remember now. There is a figure somewhere in one of the UKCP science reports that compared, I think, changes in storminess in UKCP with other CMIP 5 models, and I know there were no differences there. So that would be one. And Carol, I think you might be able to correct me on this. Am I right in saying we have downscaled 4 or 5 other CMIP 5 models using the UKCP approach? So potentially those data could be analysed for a future project to see how different they are to the main UKCP ensemble.
Yeah, there is some work in process to downscale a small number of CMIP 5, and we're looking at whether they are good enough to release as you're doing some evaluation now to consider releasing those alongside the other UKCP. So that would be, one way of capturing that extra uncertainty. That's interesting. Thanks, Mike. We got one more question from Quentin Dawson. Thanks, Mike. Good to explore, understand relevance of the output to other sectors, e.g. design standards for roads, efficacy of outdoor equipment and clothing. Is that a question? Or just a comment? Yeah. I'll let you respond either way.
Yeah, you're right. The building regulations people in government are very interested in these results. So when they're officially released, I know they'll want to take a closer look at them. Yes, and I have in a previous talk, I was approached, well, someone had put in the chat, yes, it'd be good to get the construction industry more on board in this as well. So there's potential, you're right, many potential different uses of these results. So it's just we're just trying to promote them, and yes, maybe we should try and engage with people like outdoor clothing and others as a way of, yes, future-proofing their designs and materials. That's a really interesting idea. I hadn't thought of that.
Okay. Just trying to keep track. I think some people are having problems using the Q&A, so some of our questions are going into the chat. So I'm just checking whether there's anything else to ask. No, I think that is all of our questions for today, unless I've missed any. Is it Lali? No. No. Good.
Matt Miller is asking about the signs we see in natural adjustments in our ecosystem, such as proliferation of moss or patterns of tree fall. But I'm not quite sure what the question is. I'm sorry.
I'd probably say those sort of impacts on ecosystems are outside my knowledge. I mean, generally, if you get warmer, wetter winters, you probably would expect more moss, I'd say, at a guess. But and high winds would obviously more tree fall. But I think that's probably a separate issue to wind-driven rain per se.
Yep. Thank you very much.
That's great. Okay. Thanks, everyone. I think I'll just move on now to a bit of a taster of what we've got coming up with our next next webinar. So in March, we can look forward to hearing from our very own David Viner. David, you may recognise from previous UKCP webinars because he co-chairs our DAX group and often chairs these meetings. So he'll be talking to us about understanding dynamic risk. And also we'll hear from Richard Chandler, who's at UCL. And Richard will be talking about the Euroquadex UK projection. So that's some guidance on how you might enhance the use of the UKCP 18 regional by drawing from the Euroquadex downscaled archive as well. Okay, I think on that note, I'll thank both of our speakers again. Thanks to both of you for some really, really interesting talks. Thanks everyone for joining and listening today. These are always really interesting webinars, and it's really great to see such a lot of you here coming to listen. So thanks again and enjoy the rest of your day.